Okay, so we're going to have a look at the feedback video on the recent AS chemistry mock that you did in April. So this was a second one. We've already done the first one, so that video is up and you should have viewed that and done your corrections. So same deal here, guys. Do your corrections. Okay, reflect on your learning. Okay, make sure that you know where you went wrong. Right, let's look at the first question. So first question was an organic compound. It required you to be on the ball with your skeletal formula. Okay, some of you were very much on the ball with this, some of you not so much. Okay, so if we look at skeletal formula here, we have a carbon where we have an angle, we have a carbon. Okay, where we have an end point, we have a carbon, and where we have a junction or a joint or an angle, or whatever you want to call it, we have a carbon. Okay, so this must be a ketone. This one is the same carbon, but it's got an OH group and a C double O bond group on it. That must be a carboxylic acid. Finally here we have a carbon here, attracts to a carbon on that side, a hydrogen there and a carbon oxygen double bond there. So this must be an aldehyde. So we had to be able to tell the difference between these. Okay, first of all between compound A and compound B. A lot of people here wrote acidified or wrote potassium dichromate, which is wrong. If it was to do with dichromate, it would always be acidified potassium dichromate. Anyway, A and B we can't use acidified potassium dichromate for the simple reason that neither potassium dichromate is an oxidizing agent. Neither of those two compounds, A and B, ketone or carboxylic acid, will be oxidized by an oxidizing agent. Okay, so what would you use here? You would use sodium carbonate, okay, or sodium hydrogen carbonate, or any metal carbonate. It doesn't particularly have to be sodium. Sodium is one that's used most frequently. It's very soluble, okay, and the products of it are insoluble. Okay, observation with A is that you will get no visible change in A. Don't say no reaction, please. Okay, we're looking at observations here. Okay, so there's no visible change in A. In B, you will get bubbles or effervescence, something like that. There's only one mark per thing, so we don't need to go into too much detail. Okay, we then had to tell the difference between A and C. This is where we can use our acidified potassium dichromate. It must be acidified. If you don't write acidified, you don't get the marks. Simple as that. Aldehydes can be oxidized to carboxylic acid, so that in that direction, not to that particular carboxylic acid, but to a carboxylic acid. Ketones, in terms of oxidation, they do not undergo oxidation. So the ketone A, there will be again no visible change. Aldehyde C will of course go. Acidified potassium dichromate is orange when it's reduced, or in other words, when it acts as an oxidizing agent, the colour of the solution goes green. Okay, so that was it really. A lot of us were using some bizarre things. Okay, you could have used here a universal indicator. Okay, and universal indicator for that would of course go sort of red orange, whereas a ketone is a neutral. So you could have done that. Okay, this was to do with one of our mechanisms. I think it was a couple of mechanism questions on this. Make sure you learn your mechanisms well, guys. And we had potassium hydroxide reacting with a haloalkane, and we had to outline the mechanism. First thing that you take from this is that this is a primary haloalkane. Remember, the mechanism for primaries and tertiaries is different. We have SN2 versus SN1. So let's look at the primary. We have our C2H5 group, okay, and we have bromine. In actual fact, I will draw it fully because I need the carbon there. So let's have a CH3, and then we have a CH2. Usually on our mechanism we will draw deltas, delta positive, delta negative charges if they're relevant, which they are here. Okay, and because this is a primary, this goes by SN2, so the hydroxide ion, lone pair on the oxygen and the negative charge. Okay, so let's put in some curly arrows here. Right, so curly arrows start between on the hydroxide, and they start between the lone pair of electrons on the oxygen. They have to. That pushes the electrons in the bond to the bromine. You'll note that my line here is touching the bond. That's important. It has to be touching the bond. That gives us an intermediate state, okay, or a transition state, where the bromine is sort of almost left but not quite, and the hydroxide end is sort of almost covalently bonded, but not quite. Okay, don't forget your CH3 group. That has to be represented by dotted lines. Alright? And there's an overall negative charge on that. The last thing that happens is that the bromine does in fact leave. Okay, and we end up with this molecule here. It then asks you if the name of that molecule is called ethanol. Some of you call it ethanol. Okay, I think you'll probably get marked wrong for that on an exam, but I'm not 100% sure, but I certainly wouldn't be writing. I mean, you can't have ethanol, there's no such thing. You'll not have seen it. Okay? Right, let's have a look at the next one where we're asked to calculate out percentage atom economy. And remember what a percentage atom economy is, guys. That is percentage AE, or atom economy, okay, is equal to the mass of the desired product divided by the mass, the total mass of all products, times 100. So the mass of your desired product is your ethanol here. That is a mass of 46. All your products together are 46 of the ethanol plus the potassium bromide, and that gives you 165. And you times that by 100, and that gives you 27.8 as your percentage atom economy for that question. Okay, let's have a look at this. This was a really good question, and when I say good, I probably mean a difficult question. So what they did here, normally in these questions, what we do is we're asked to work out the delta H, and we get our Q, which is equal to MC delta T, and we take our Q and we divide it by the moles of the reactant, and that gives us our delta H. However, here what they've done is they've switched this around a bit. They've given us delta H, and they've asked us to calculate out delta T. Okay? Now, they've actually asked us to calculate the maximum temperature rise, which is the original temperature plus delta T. So there's a little bit more to it even than what I just said. Okay, so how do we go about getting our delta T? Well, to get delta T, we're going to have to get Q. To get Q, okay, we're going to get that from delta H. So if we remember, delta H equals Q divided by M. Now N is number of moles. Q is the heat energy given out in the MC delta T calculation. Okay? So therefore, if we rearrange this, okay, we can get Q equals delta H multiplied by the number of moles. Right, the number of moles is what? Well, the mass of the cyclohexane that's burnt started off at that, 192.73, went down to 192.10. Okay, so that is 0.63 of a gram of cyclohexane. Now, cyclohexane, as it tells you in the question, is an RFM of 84. So that means the number of moles involved here of cyclohexane is 0.0075. So there's our moles. Alright? Now we've got to go and try and get our Q value. Okay? So the Q value, as we said here, is equal to delta H multiplied by the number of moles. So we take that and we multiply it by the delta H, which is 1216. Alright, and that gives us 9,120 joules. That is our Q value, that's the number of joules. Now we're looking to get delta T. Okay, so if we know that Q equals MC multiplied by delta T, we can rearrange that to say delta T equals Q over M times C. M we know is the volume of water, mass of water, sorry, that's absorbing the heat. So Q is 50, M is 50, sorry. C is down here, it's given to me at 4.18, and I know my Q value up here is 9120. Okay, so all I've really got to do now is plug those values in, and that gives me the delta T. Yeah, so my delta T, alright, works out at so my delta T works out at 43.6, but remember they're asking us for the final temperature. So the initial temperature is 19.1, so it's 19.1 plus the 43.6. So my final temperature in that would come out of 62.7 degrees Celsius. So very good for those of you who got that correct. Right, the next one then, where they're asked that the student was told the enthalpy of combustion cycling hexane was that, and the student concluded that the temperature rise recorded in his experiment was smaller than it actually should have been. So why would that be the case? And we have to give a practical reason. Okay, so it has to be a practical reason. Right, so, well, some things could have happened. If we go back to here, cyclohexane is quite volatile, so some of that could have actually evaporated rather than burning. Okay. The other thing is that some of we're relying on complete combustion here, that's what we're assuming, but some of it could of course have undergone incomplete combustion because there simply isn't enough oxygen available. Okay, and the last thing is, of course, you know this reaction, and you know that you carry it out on a little burner, that's meant to be a flame there, and the heat rises up to the water. Okay, well, you know that heat can be lost through convection currents, carrying some of that heat from the flame, not into there, okay, but being lost to the environment. So there's three ways that you could have ended up with less heat energy than you may have hoped for. Okay, right, let's look at this. We're going to use the data to calculate the enthalpy change for this particular reaction. Okay, so the reaction that we're after here, we've been given standard enthalpies of combustion here. So for standard enthalpies of combustion, that means carbon is going to go to carbon dioxide. We'll have 6 of them. Hydrogen is going to go to water. And when you combust hexane, it's going to go to carbon dioxide and water. So there's your link. Now, if we put our values, every time I burn 1 mole of carbon, it's minus 394. I'm burning 6 moles of it here. Every time I burn 1 mole of hydrogen, it's minus 286. I'm burning 6 moles of it here. Every time I burn 1 mole of hexane, it's minus 3920, and I am only burning 1 mole of it here. So that's fine. Now, in Hess's law, what we want to do is we want to go from here to here along the blue arrow, but we want to go on an alternative route, which is this route here. So our calculation for our delta H is minus 394 multiplied by 6 plus minus 286 multiplied by 6. Right, now this arrow is going against us. Our blue arrow wants to go from reactants to products. That's going against us. So what we do is, instead of adding that, is we take that away. So that is minus 3920 or plus 3920. The answer there comes out at minus 150 kilojoules per mole. Some of us were getting this answer as a positive value, which costs you a mark out, so just be careful. Careful with your math. Sorry, it's actually 160, not 150. Okay. Right, the complete combustion of octane. Well, this is very disappointing for people who got this wrong. So octane has that formula. It's combusting, so it's going to oxygen. It's complete combustion, so the products are carbon dioxide and they are water. We balance this in alphabetical order, so carbon's first. I need an 8 there. I need a 9 there. Okay, that gives me 8 times 2, 16 oxygens there. Over here it gives me 9 times 1, that's 9 oxygens there. So I've got 25 oxygens that I need to balance 12 and a half. Now the other thing, you could have had all of those, if you wanted, you could have had all of those values doubled and made the oxygen into whole numbers, but I don't recall anybody doing that. Right, catalytic converter getting rid of nitrogen monoxide. Well, there's a few. The one I think that most of you used, which was good because it was in my notes, was that. Okay, that was fine. Some of us used, I think this one, not very many of us, to give us N2 that is, plus 2CO 2, and that was it. I don't think I saw any other, any other alternative answers that I saw were incorrect as far as I could see. Okay, another calculation. Okay, I think we're getting the message that there's going to be plenty of miles in these papers, so we need to really brush up on them, guys. So we're getting sulfur dioxide produced in an industrial setting. Okay, and we are getting 6.49 million tons of it. Okay, produced every year, and what we had to do was work out the mass of the calcium oxide, and it had to be given in kilograms that was needed to neutralize all of that sulfur dioxide. So of course we had to take our 6.49 million tons, and we had to take our 6.49 million tons and turn it into, of course, moles. Okay, so 6.49 million tons. Okay, so there's 1,000 kilograms in a ton, there's 1,000 grams in a kilogram, so this is 6.49 million grams. That makes sense. Okay, so we had to take million grams, sorry. So we had to basically multiply that by 10 to the 6, okay, and that gives us 6.49 times, gives us 6, get rid of that, 649,000 times 10 to the 6. Okay, and we divide that by the relative atomic mass of our sulfur dioxide, which is 64. Okay, now that gives us a total number of moles, okay, of 1.012 times 10 to the 11. Now the ratio of sulfur dioxide, that's moles of sulfur dioxide. The moles of calcium oxide are the same, they're a 1-to-1 ratio. So if we took that moles of calcium oxide, okay, and we multiplied that by the RFM of the calcium oxide, which is 56, okay. Now remember, we're working in grams at the minute, so whatever this answer is, we're going to take it and we're going to divide it by 1,000, because the answer asks us to give our answer in kilograms, okay. And that comes out at 5.68 times 10 to the 9, of course, kilograms. Okay, this time we were showing back to organic here. We're looking at the hydrogen bonding in a molecule of methanol. So what they're after here primarily, guys, is the fact that this is delta negative and this is delta positive. The other important thing that you want to show here is that the oxygen has 2 lone pairs on it, okay? So we can do it by just doing 2 dots or those little lobes. Now where is the interaction? Okay, well if I take another molecule of methanol, okay, and I do the same, delta positive, okay, the hydrogen bond runs from the lone pair to the delta positive hydrogen. That's where it runs, that's where they want you to show the hydrogen bonding, okay? Right, it then says that the bond angle around the oxygen atom in the methanol is smaller than the regular tetrahedron. Why is that bond angle smaller? Well, that's simply because, okay, around here you have 2 lone pairs. So the oxygen, which has 2 lone pairs, okay, that is going to cause the hydrogen, and in this case the carbon, okay, to have a smaller bond angle than what you might expect. And that would normally be 109 for the tetrahedron. This one's going to be less than 109 degrees. Okay? And you talk about repulsions between lone pairs being stronger than repulsions between bonded pairs. Okay? So I think some of us talked about the atoms being squished or squashed into a smaller space. That's really bad use of language for a chemistry paper, guys. You simply will not get away with that. Okay, this mechanism here, it is propane with concentrated acid. We can see it's just been added to it, so that you are aware of an addition reaction called electrophilic addition, and that is what it is. You study that, and this is just a variation on that. So you get a mark for electrophilic, a mark for addition. You then had to draw the structure of F, okay, which was just simply the other structure. So if this was propane, it could, of course, if we just draw propane quickly, okay, so in this instance the sulfuric acid is added to the second. All you then had to do really was draw the same thing, but with the sulfuric acid on the third. So in this case it would have been CH2, CH2, CH3, and then on this one we have our same structure as we have on the answer or the question here. So that would have been your answer there. You could have drawn it as skeletal formula or just as, but all your bonds had to be right. That had to be right. So explain why more of isomer E is made than isomer F. Well, if we look at isomer E, which is here, and then we have now got F here. So isomer E, if we work out the carbocation that isomer E must have come from, okay, must have been that one, okay, and then if we work out the carbocation that this one came from, okay, so we'll see that is secondary for isomer E, and for isomer F this is primary. We've got to talk about the fact that isomer E is made, okay, and it's made via, it is not, some people said it was a secondary carbocation. It's not, it's made via a secondary carbocation, okay, and that the fact is that the secondary carbocation, I should say, is more, so just secondary carbocation is more stable than a primary carbocation. Okay, so you can't say these things are secondary, you can't say these things are primary carbocations, they are made via, that's the mechanism, and that's where your explanation must lie, guys. Right, skeletal formula of propan dioic acid. That was fairly straightforward. Most people did pretty well here. I'll just draw it out sort of full, and just for those of you who didn't maybe get it right, you can perhaps see. Right, so remember in skeletal formula we don't draw carbons and we don't draw hydrogens unless they're attached to oxygens. If they're attached to carbons we don't draw them. Right, so we've got 3 in our carbon chain, so there's our, how we draw 3 in our carbon chain, yeah? Okay, now at the end of each chain we have an OH, so we draw the OH, put a bond to it and we draw it. Each of these carbons that are at this junction here and here have got a double bond going to an oxygen. So that's how we convert our propane dioic acid into our skeletal formula for it. Okay, describe how you would prepare 250 cc's of this aqueous solution. So this is straight out of your practical. Alright, very important that you learn your practicals, guys. This one was worth a massive 6 marks, so 10% of the entire paper. So really, really important. Right, first thing you do is you weigh, okay, weigh the sample, so the measured out sample that you may have to work out into a weighing boat. Alright, or similar, it doesn't necessarily have to be a weighing boat. Okay, the next thing you do with that is you transfer it. Okay, and that's transferred to just into a beaker. Alright, and then you either do 2 things, you either wash the boat into the beaker, or you go back and you re-weigh the weighing boat. Either way you're making sure you know exactly how much of the solid has made its way into the beaker. The next thing you do is you dissolve that solid, which you put into the beaker, okay, and you dissolve it in a minimum, okay, minimum volume of deionized water. Okay. Now that, if you do specify a volume, it must be less than 250, right? 250 cubic centimeters, because your volumetric flask and the volume you're making is only 250 at maximum. Okay, so if you do specify a volume, it must be less than that. Right, you then transfer all of that, and you also transfer the washings from that into a 250 cubic centimeter cc, not cc, a volumetric flask, and you must quote the size of the flask. Okay. What do you do now? You very simply, your last marks will be shake it and invert it. Not just, a lot of people are just writing invert it. You must shake it and you must invert it. Okay? And that gives you your homogeneous solution that you would be after. So those were your points, guys, okay? You had to have all of those to get all six of your marks, okay? Right, then you had to calculate the mass of the magnesium. Okay, sorry, the mass in milligrams of the propanoic acid required, okay, to prepare this solution. Okay, so again we have another calculation. Alright, so please cotton on to the amount of calculations that we're after, guys. Okay, so how many moles do we need? Well, N equals C multiplied by V. So the C is 0.005, the V is 0.25. Okay, that means the moles of propanoic acid that we're going to need to make this up is 0.00125 moles of propanoic acid. Okay, if we take that and mass equals moles times RFM, we multiply that by the RFM, it's 104, okay? And that gives us 0.130 grams. But remember, the question's in milligrams, we've got to multiply that by 1,000. So our final answer should have been 130 milligrams. Okay, here we go, another calculation, alright? So this time we had to calculate the minimum volume, so just remind yourselves, this is a solution, okay? Potassium dichromate, acidified potassium dichromate is of course a solution, so number of moles equals concentration times volume, so volume equals moles divided by concentration, okay? So we've got our concentration of it here, okay? We've got to get our number of moles, which will allow us then to convert that into the volume, right? So the moles of the propanol I can get first of all, okay, which will allow me to work out the moles of the potassium dichromate. So the moles of the propanol, we've got the density of it and we've got the volume of it that was used. So mass equals density times volume, which is of course 0.8 multiplied by 6. So that, okay, and then that gives me the mass. And then if we take that and we divide that by the RFM of the ethanoic, of the propanol, which is 60, that gives me 0.08 moles of the propanol here, alright, and that means that I will need that divided by 3, because look at the ratio here, and I think a lot of us didn't pick up on that. The moles of dichromate is a third of that, okay, that comes out at 0.0267 moles of dichromate that we would actually need. The volume of dichromate, then if we go back up to here, volume equals moles divided by concentration. Concentration is 0.40, okay, and that comes out at 67 cubic centimeters whenever we did that, okay. If we multiply, so that will come out, it will come out at 0.067 there, which is in decimeters cubed, and we would convert it into centimeters cubed because the answer, the question, sorry, expects it to be in cubic centimeters. If you left it in decimeters cubed, you would lose one of your 3 marks. Okay, the last structure question that we were looking for, how do we convert propanol from propan-1-ol? If we remember, propan-1-ol is a primary alcohol. That will be oxidized to an aldehyde, and if we leave it in contact with the oxidizing agent, it will go to a carboxylic acid or an oleic acid, yeah? Now, we don't want this to happen, we want it to go to here. So we've got to draw distillation. If you drew reflux, you threw away all the marks. So distillation, how do we draw distillation? Right, first of all, we have coming up out of here, we call a side arm, and this diagram is in your notes. Okay, oh sorry. So the side arm takes it out. Okay, and this has to be stoppered. Okay, now that brings us across to a horizontal Liebig condenser. Now that has to be sloping down because the vapours and the liquid has to move out of that and drip down. Right, that has a water jacket around it where the water is going in at the bottom there, and the water is coming out at the top. I had a lot of condensers with no water jacket at all. So the condenser is there, water's in at the bottom, out at the top. Okay, we then have something like a delivery tube, okay, going into could be a conical flask. It doesn't really matter what it is. Okay. Alright, so those were sort of all the things that you had to have. We had water going in at the bottom, out at the top. We had our condenser sloping downwards and being horizontal. Okay, the condenser, just the other things that were that are on the mark scheme for this were that we had to have an open end here. We had to make sure there was no blockage. Some people had like a line going down there, which was a blockage, and that cost you marks. Some people had gaps, maybe in these little joints here. Those gaps, if they were there, those would also cost you a mark. Okay, and that was about it really. So that was worth 3 marks. Pretty easy 3 marks, guys. But those diagrams are in your notes, they're in your textbook, they're in your revision guides. So make sure to remember them, please. Okay, a drink. So we're into the multiple choice then. So a drink driver. Okay, we're looking to calculate the concentration in his blood of moles per decimeter cubed. So we've got 80 meg. So I would just convert that into grams straight away. And that's 80 over 1,000. Okay, so 80 divided by 1,000. Okay, is the mass in grams then of the ethanol. So divide that by the RFM of ethanol. Just convert it into grams because remember RFM is in grams and therefore it has to be done like so. Okay, and that gives me, a value of 0.00174. Okay, that is my moles. Remember the other one, we're looking for concentration. Concentration equals moles divided by volume. So if I take that and I divide it by 0.1, which is the volume here, 100 cubic centimeters. Okay, and that gives me an answer of C. Right, which statement is correct for the distribution curve of the molecular energies? Okay, so the answer to that, the curve is symmetrical about the maximum. No, it definitely is not. It's sort of kind of like that. So that's the maximum. It's definitely not symmetrical right there. There are always some molecules with 0. No, there are 0. It goes at the 0, 0 axis here. So there are 0 molecules with 0 energy. The position of the maximum of the curve is not dependent on temperature. Okay, well, it's not. It's dependent on the number of molecules. Remember the peak here, the maximum is dependent on the number of molecules, not the temperature. So the final answer, the mean energy of the molecules is greater than most of the probable energy of the molecules. No, it's definitely not. So the answer is D. Okay. Right, this one here, then this molecule here was 1, 2, 3, 4 carbons. We have hydrogen, 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 hydrogen. So it's 4 carbons. It is 8 hydrogens and an oxygen. Now if you go through all of these, you'll find that this one down at the bottom here has 4 carbons for sure. Yeah, that's fine. It has only got 6 hydrogens though, so there's no way that and that could be isomers of each other. All the others can be. Right, how many isomers are there of this? This was probably a really tricky question, but this is a question that's designed for the very most able. So let's have a look. Okay, so we could have just a normal amide, okay, NH2. We could have the nitrogen in the middle with the CH3 there. That's CH3 there. Remember, nitrogen can have 3 bonds. That's CH3 there. Okay, we could also have a nitrogen just with 1 hydrogen, CH3 there, and a C2H5 there. And the final one we could have was sort of a chain isomer of that, or we could have NH2 at the end of carbon. We can take that carbon off the end though, and we can put it there. Okay, so that was 4. 4 was the answer. Difficult question. Which one's a propagation step? So propagation steps have molecules and radicals to give you molecules and radicals. The only one that does that is molecule, radical, radical, molecule. So the answer had to be D. This one is a termination. 2 radicals making a molecule. 2 radicals making a molecule. Termination. This is initiation. A molecule making 2 radicals. Which compound would react with ammonia to produce propylamine? So propylamine is 1, 2, 3. NH2 group on the end. Okay, that's done in your haloalkanes section. Okay, when you go back to the original molecule that comes from, you would swap that with a halogen. The only one that does that is that. Okay, so that's 1 bromopropane. Right, which statement about the following is not correct? Okay, so right, so it displays EZ isomerism. Well, very quickly you should be able to pick up there's a CH2 on the end of where the double bond is. So a double bond will allow EZ isomerism, but when you get 2 hydrogens on 1 carbon here, you can't get EZ isomerism because you always need 2 different groups at those 2 X's. Okay, so the answer was straight off A. Which compound can be oxidized to form the following? Right, well let's draw out this, okay? So we have a CH with 2 CH3s on it. I always like to draw my CH3s at the end if I can. Okay, then we have a CH here. Okay, sorry, a C double O bond there and a CH3 there. Okay, so which compound could be oxidized to form that? Well, this is going to come from an alcohol, so I would draw out the alcohol, which would be wherever the ketone group was. Okay, you would have the OH group. So we're now going to have an alcohol with the OH group on position number 2 and a methyl group on position number 3. Okay, so the answer had to be D. Which one can act as a nucleophile? Remember, nucleophiles are attracted to areas of dense positive charge. So it isn't going to be that. It isn't going to be that. This methane is a completely symmetrical non-polar molecule. It isn't going to be that. The CH3, which you actually drew out earlier with the lone pairs and the delta negative on it. Okay, well it could potentially, because of its lone pairs and the delta negative, it could indeed be a nucleophile. Which alcohol forms a mixture of alkenes when dehydrated? Okay, well, you if you know that the 1, anything with a 1 isn't going to do that. So if we looked at propan-1-ol, the only double bond you're going to get could possibly be here. Okay, can't be anywhere else. So anything with a 1 in it, you can just get rid of. Okay, let's look at propan-2-ol. Okay, well, propan-2-ol will give me an OH here. Okay, sorry, OH there. Now I'm going to get either a double bond there or a double bond there. Doesn't make any difference. The product is still going to be exactly the same. Let's look at pentan-2-ol and let's strip the OH out of it. Okay, so dehydration will give me a double bond there or a double bond there. Get rid of that. Okay, so if I had the first one, I'm going to get, you can see pentan-1-ene, and the second one is of course going to give me pentan-2-ene. So the answer is D. That's the only one that would give you a possible mixture of alkenes. Which one's a has boiling point? Right, so they're pretty much all got similar van der Waals. This one has dipole-dipole. This one has got dipole-dipole. This one has got dipole-dipole. This one has got a C double O bond, so that's going to have dipole-dipole. But it also has an OH bond, so it's going to have hydrogen bonds also. That's your answer. Which compound could not be produced by reacting 2,3-methyl with sodium hydroxide? Right, sodium hydroxide, okay, will do a couple of things. Okay, sodium hydroxide can replace the bromine with an OH, and it can also carry out elimination. Now it's fairly obvious elimination does happen here, because all my products apart from this one are going to be alkenes. Okay, so let's draw out our 3-bromo here and a methyl group there. Okay, right, so let's look at elimination. Elimination will remove the bromine and a hydrogen beside it, on a carbon beside it, sorry. So it could be that one in the square box, or it could be that one in the square box. Right, well let's remove this square box here first and see where that takes us. Okay, so that gives us a 3-methyl and a but1. Okay, so 3-methyl but1ene, okay, could not be produced. Well, there's 3-methyl but1ene there, so it could be produced. Okay, let's take square box number 2 here off that hydrogen off it as well as the bromine, sorry. Okay, so that's the bromine has now gone, one hydrogen left. Here we have a CH3, okay, and we have a CH3, pen's gone wonky, that's a CH3 on the end. Okay, let's look at this. Here we have a methyl at number 2, and we also have our alkene at number 2. Okay, well there's that one there. Okay, so we are going to be able to get that one. The next one then would be where the Br is replacing the OH. Okay, or sorry, the OH is replacing the Br. Would be that one. So that is a alcohol in position number 2, and a methyl group now is pushed over to position number 3. Okay, well there you go, that's that one. So the answer must be here. We can't, there's no way that we can get that. So the answer is A. Right, which compound produces this spectrum? Okay, so this was quite sneaky. This value here runs right to, excuse my wobbly hand, but it goes to about 1850. So some people said to me, could this not be, I think, what they asked me, it could be a C double bond perhaps, but the C double bond was in a slightly tighter parameter than that. This one quite clearly ran from about 1600 to about 1850 if you looked at it carefully. That meant it had to be a carbon-oxygen double bond. This here then was an OH group, but it was an OH group from an alcohol, not a carboxylic acid. Carboxylic acid is much broader, runs sort of down to about there, yeah, and incorporates the CH bond there. So this was something that had a carbon-oxygen double bond, and it had an OH group, okay, from an alcohol. So it had to be B4-hydroxy is the OH group, and butanone is the C001. It's the only one that had both of those groups. It couldn't be ethanoic acid for the simple reason that the peak was not broad enough to be ethanoic acid. Okay. Last but not least, this rather challenging question. Hopefully when I draw it out here you'll see that it actually wasn't too bad. Right, so the heat release for 1 gram of ethanol, okay, MR46 undergoes, when it undergoes complete combustion. What we had to do was calculate out the heat released by each molecule in joules when ethanol undergoes complete combustion. Right. So complete combustion is per 1 mole of the thing. So the first thing that I would do here is take 29.8 and multiply it by 46. 46 is the MR of ethanol. 1 mole gives you 29.8. So, sorry, 1 gram gives you 29.8. Okay, so therefore 1 mole is going to give you 46 times that. I would also take that and multiply it by 1,000 because your answer is to be kind of given in joules. This value here is in kilojoules, so I just convert that over into kilojoules. Okay, so that comes out at a fairly large number, as you would probably imagine. That is joules now, and this is joules per 1 mole. Now remember,
how many molecules are there in a mole? There's the Avogadro's number of molecules per mole. So this is the Avogadro's number, okay? So this is how many joules we get per 1 mole of the thing, okay? And we've got to work it out per 1 molecule. So we've got to take this and divide it by the Avogadro's constant to get it to per 1 molecule. And that comes out at 2, because at the minute it is per mole, which is 6.02 times 10 to the 23 molecules. We need it just per 1 molecule. So that comes out at 2.28 times 10 to the minus 18. The answer is A. Okay guys, hope that helped. Any questions or queries from it, okay, please ask me. I hope it's a good learning experience for you. It's those 2 difficult tests you did, okay, so you guys need to go now, get the heads down and get revising, okay, and bring any problems to myself, Mr. Smith, or Mr. McNaught.